So today I'll be mostly trying to relate what I've shared about linear algebra from the start up to where we have reached now. Last weekend we looked at solving a system of linear equations using using elimination and back substitution. Last time we specifically looked at an equation similar to this one. Yeah, but today I want to bring together all we have been looking at. So some of the things we looked at were basis vectors. Basis vectors. We looked at basis vectors as the first thing we looked at was vectors. We can represent vectors as a column of numbers x, y, or in a two-dimensional system, or x, y, z, and so on. Then we also looked. That's what we looked at vector. Then we looked at we looked at special vectors called basis vectors, and we realized that basis vectors, for example, in a two-coordinate system, were they were they were the vectors I hat and j hat. They were the vectors I hat and j hat, which were 1, 0, and 0, 1. And these vectors can be used to represent any other vector within this space as a linear combination of these vectors. We also looked at linear combination, of course. Linear combination is simply multiple. Let me just say linear combination. Linear combination of vectors. We looked at linear combination simply multiplying a vector by a scalar and adding them. And linear combinations enable us to represent any vector within within the space as the basis vectors. For example, if we had a vector here, it could be represented as a. I'll not dive too deep into it now. I'm just refreshing us. So if we had any vector here, we could represent it as a linear combination of I hat and j hat. And we realized that if somehow we also looked at linear transformations. And we realized that linear transformations represent kind of moving space. I'll be using a 2D example. A linear combination can mean rotating this space, or simply maybe moving this 2D coordinate system to anywhere, or perhaps rotating it, or even sharing it in some kind of way, basically manipulating space. And every time you move space, the vectors change positions. And let's say if this vector, let's call it our vector v. If this space was transformed and this vector v moved to maybe another position here to v2, and we realize that this vector, if we know the new positions of I hat and j hat, we can simply perform a linear combination on I hat and j hat using the values of the former vector as scalars to get the new position of v2, and realize that the new positions of I hat and j hat can be packaged into what we call a matrix. So a matrix linear represents a linear represents a linear transformation. We use matrices to represent transformations. And a matrix is usually the new positions of I hat and j hat, and we can multiply that matrix by any vector to find its new position after the transformation. So that brings us to linear transformations. So that's a brief reminder of basis vectors, linear transformation, matrices, vectors, and linear combinations. Then last week we looked at solving a linear system of equations, and we saw that this system of equations can be represented as a vector matrix multiplication. This equation can be represented in this form, where we have our matrix. Matrix, we get it from the coefficients of all the unknowns. The coefficient of x here is 1, here is 2, and z is 1. 3 is x here is 3, y here is 8, z here is also 1. Since we have no x, we have a 0, and our y here is a 4. Our z also a 1. This matrix that represents the transformation that was applied our x, y, z to get the values 2, to get the new vector 2, 2, 12, and 2. So we looked at how we could represent any system of linear equations as a matrix vector multiplication to get our final vector, which is this. So we can look at this matrix as A, this as our B to get the final vector C. Then we looked at how we can use elimination and back substitution such that we find out which vector B, the transformation of matrix A was applied to get that. That's how all we have looked at so far is related. I don't know if I should go again through the elimination process, but I hope it was clear from the video. Then next week, hopefully, we can look at into depth Gaussian elimination and row echelon in solving linear systems of equations. This week, hopefully I could try to relate everything. And if you had any questions of what you had not understood in all that we have looked at,